Okay, so me and Yuling are doing the tree diagram project for week 11. Let's let Yuling take it away for the introduction.
So, we are given with the scenario. We are solving a probability problem to determine how likely it is that someone who tests positive for a new disease and actually has it. So, we are given that the disease is very rare, affecting only 1 out of 4,500 people. The test is 99.7% accurate at detecting the disease, but it has a 6% false positive rate. A false positive means the test says someone has the disease when they don't. So we want to figure out, if someone tests positive, what is the probability that they actually have the disease?
So, step 1, or building the tree diagram. So we start first with one bubble start, and this splits into 2 branches, as you can see on the right side, where it says has disease, A, and does not have disease, A to the power of C. From each of these branches, we can add 2 more branches for each test result, positive test B and negative test B to the power of C. And let me explain the probabilities for this. The first split is based on the chance of having the disease. This P of A value is 1 over 4,500, or 0.000222, which is really rare. And the P of A to the power of C is equal to 1 minus 0.000222, which is 0.999778. And this second split, which is next on the right, is about the test result. If a person has the disease, A, and the test correctly says positive, 99.7% of the time, the probability of A given B is 0.997, and the negative 0.3% of the time of probability of A given B to the power of C equals 0.003, which is basically a negative test on the top of this tree diagram to the right. And the same thing goes for the bottom of the side, where if a person does not have the disease, or A to the power of C, the test falsely says positive 6% of the time. The probability of A to the power of C given B equals 0.06, and the negative, which is 94% of the time, or 0.94, is the probability of A to the power of C given the probability of B to the power of C, which is 0.94. So, the tree starts with has disease or no disease, then splits again for positive or negative test results.
After creating our tree diagram, we now look at the endpoint joint probabilities, which is a combination of events. For example, has disease and tests positive. To calculate the probability of each endpoint, we multiply the probabilities along the path. So for the first endpoint, we have the probability of has disease and tests positive. And to get this probability, we multiply has disease and get tests positive, the probabilities of those respective conditions, which gives us 0.0002213. Our second endpoint, which is has disease and tests negative, we get that by multiplying the probabilities of those two, which gives us 0.000000666. And for the probability third endpoint, which would be no disease and test positive, we get 0.0599867. And lastly, the last endpoint would be no disease and test negative, would be 0.9397913. So now we have probabilities for all possible outcomes, but we're only interested in cases where the test is positive, which is P of B.
So after Yuling calculated the probabilities, we now can apply the Bayes' theorem. The Bayes' theorem is to find a probability of having the disease given a positive test. We use Bayes' theorem, which is probability of B given A is equals to probability of A and B over probability of B. I'm pretty sure that sign of an upside down U is and. If not, please correct me. Anyways, first we calculate the probability of B, the total probability of testing positive. This happens in two ways: has disease and test positive, or no disease and test positive. So we add both of these probabilities. The probability of B equals probability of A and B, and the probability of A to the power of C and B, which is equal to 0.0002213 plus 0.0599867, which is equal to 0.060208. So all these numbers sound really confusing, but then after you get that value of adding the probabilities, you then use a base formula to calculate probability of B given A, which is after substituting 0.002213 over 0.06028, which is approximately 0.3676. What this means is that if someone tests positive, there's only about a 0.3676 chance they actually have the disease. So this problem shows why we should need to be careful with medical tests for rare conditions, because high accuracy isn't enough if there's a high false positive rate and the condition is rare. Thank you very much, and that concludes our presentation.